Hello, I'm Ashim Sen Gupta. I'm a PhD student at Queen Mary University of London, and today I will be talking about nonlinear Horndeski analysis with HiCOLA. This is work I've done alongside Dr. Bill Wright and Dr. Tessa Baker, who are also at Queen Mary. In a nutshell, HiCOLA is a fast, approximate simulation package that can provide results that are valid on mildly nonlinear scales for a wide class of Horndeski modified gravity theories for the first time. If there is any message I'd like you to take away from this talk, it is primarily this one. The outline for this talk is as follows. I will first motivate why we have developed HiCOLA. I will naturally talk about what HiCOLA is. I will then describe the theories that HiCOLA computes predictions for, namely the reduced Horndeski class of modified gravity theories. We will then go over an example from this class, the cubic Galilean. We will discuss the application of HiCOLA on the cubic Galilean, and in so doing, we will find a schematic overview of how HiCOLA works, and we will also go over some of the physics we have found through our usage of HiCOLA. And then before concluding, I will go over another example from the reduced Horndeski class, discussing what we have found by applying HiCOLA to that model, the extended chip symmetric model. So what is the purpose of HiCOLA? Lambda CDM has been shown to hold to high precision in, for instance, solar system tests. And for that reason, modified gravity theories that have screening mechanisms are attractive to some because they can satisfy the constraints that come from these high precision tests. So they are still viable as of current observations. Screening mechanisms are properties of modified gravity theories where the behavior is dependent, the behavior of the extra degree of freedom, the scalar degree of freedom, is dependent on the environment. It's dependent on the local density. And so when the local density is high, the screening mechanism acts to suppress the action of the scalar field, and therefore the behavior of the modified gravity theory returns to something that looks practically like GR. And that's why they're able to evade these solar system tests, for example. And screening mechanisms manifest on nonlinear scales. So this means that if we were to consider a linear perturbative analysis of our modified gravity theory with screening, we would neglect the screening property of that theory. So we have to go beyond the linear level in order to see screening in action. And typically what this involves is a numerical study of your modified gravity theory, and this means having to go through and perform computationally expensive n-body simulations. So these are expensive temporally, they can take a long time to run, and the hardware to run them can also be expensive. And so HiCOLA is a fast approximate simulation package for theories of screening because it can provide results that are valid on mildly nonlinear scales. And using HiCOLA, we can give predictions to compare with upcoming galaxy survey data to constrain this theory space of modified gravity theories with screening. And for some of these theories, will be for the first time. So what is HiCOLA? HiCOLA stands for Horndeski-in-COLA, and COLA stands for co-moving Lagrangian acceleration. It's a hybrid n-body code that uses Lagrangian perturbation theory on large scales and an n-body part on small scales, and the marriage of the two give mildly nonlinear results in less time steps than traditional n-body codes. And what we can do is we can incorporate and compute predictions for theories with screening by encoding modified gravity as a fifth force effect in these COLA codes that were originally designed for GR. Here I've taken a figure from the paper that first introduced COLA, and you can see here that COLA produces a result that looks remarkably like Gadget, a traditional n-body code, in far fewer time steps. So this is representative of the kind of speed up we can get by using a COLA approach. So what theories is HiCOLA designed to work with? HiCOLA works with Horndeski theories, specifically reduced Horndeski theories. So these are Horndeski theories where the gravitational waves travel at light speed. And that's because we study these theories because of the constraints coming from GW170817. So just to briefly describe this action, phi is the extra scalar degree of freedom that isn't present in GR. the red term, the G4R term, is your GR-like piece, so that's the Ricci scalar and a conformal scaling. The K term, the green boxed term, is the kinetic term for the scalar field. The yellow nonlinear term is a nonlinear interaction term that is one of the ways in which a reduced Horndeski theory can possess screening. And this is the kind of term that would be neglected if one performed a linear perturbative analysis of a reduced Horndeski theory. And the point here is that HiCOLA has been designed to be applicable to any model that is described by this action. So by design, HiCOLA is generic, and we hope that it'll be used to study and compute predictions for a wide number of models in the reduced Horndeski class. So K, G3, and G4 are free functions that need to be specified by a user in order to get specific results. So let's make some choices for K, G3, and G4. So we can take a look at the cubic Galilean. So this is a useful test case, even if it has been ruled out as a cosmological model. And perhaps the cubic Galilean is familiar to some because it's been studied quite extensively by the community. So the cubic Galilean is specified by the following choices for K, G3, and G4 as shown on screen. And here in this plot I'm showing what the background looks like, the expansion history, what that looks like for a cubic Galilean with different initial conditions. That's why there are a number of colored curves, and the black dashed line is lambda CDM for reference. So F, just to give a description, F is a parameter that controls how much of dark energy today at A equals 1 is sourced by a cosmological constant and how much of it is sourced by the scalar field. So if F is 1, for instance, that means dark energy is solely composed or solely made up of the scalar field. And if F is 0, then that means only the cosmological constant contributes to dark energy. So let's take a closer look at these at this background data. So first of all, let's take a look at the Hubble function. So we can see the Hubble function for the Galilean is decreasing, just like in lambda CDM, and at late times there is good agreement. We can see that the energy density for radiation is also decreasing with time, and again, at late times, good agreement with lambda CDM. We can see that there is a period of matter domination, so the energy density of matter approaches 1 for some period of time, but then as we approach today, it falls. And as it falls, we see that the dark energy density rises, and therefore near today we get what we see, which is the dark energy dominated phase of the expansion history. And obviously, as I mentioned before, in this case, dark energy has two components. It's the scalar field and the cosmological constant. How much and the fraction of that is determined by F. So we can see here that these cubic Galileans, they have the right qualitative behaviors. They have the right domination phases, and therefore we think that these models are of interest to study. We want to see how these models look on those mildly nonlinear scales. We want to see what their power spectra look like, because their background data is roughly consistent with the lambda CDM-like behavior we've otherwise been observing. You might be wondering, why were we so keen on looking at the background data for these cubic Galileans? The reason for that is because to complete a HiCOLA run, 3 components are computed on the way to the final result, which is the matter power spectrum. We need the modified background data for our modified gravity theory, for our reduced Horndeski theory, and we just saw that. So we just saw the background data for the cubic Galilean. We need the modified growth factors for our reduced Horndeski theories, and I won't discuss this today, but you can read up about this in our paper, certainly. And we need the modified forces between the dark matter particles of the n-body part in the HiCOLA simulation. So we are able to construct an expression for the total force experienced by 2 particles, 2 dark matter particles. And what we've done is we used the quasi-static approximation and a spherical approximation. So we've seen that the matter is spherically distributed to come up with an expression for the total force experienced that is shown schematically on screen. So the total force is proportional to the usual Newtonian force, which is coming from your usual GR, the GR part of your theory, and an extra fifth force contribution, which is coming from the scalar field. So that's the 1 plus beta s term that is also sitting now in this expression. So beta is what we call the coupling constant. This determines the total strength of the fifth force, and it depends only on the background quantities of our reduced Horndeski theory. And S is what we call the screening coefficient. This is a term that controls when the total force approaches full strength or if it looks fully screened. And S depends not only on the background but also on the local density. So this is how the screening mechanism is manifest in the HiCOLA simulation. It comes through via this S term. So you might be curious as to what beta and S look like, perhaps for a cubic Galilean, and I can show you. So here we have the curves for beta and S as functions of redshift, and also in the case of S, we've chosen some values of the density so that we can actually plot it as just a single, so that we can just plot it as a function of redshift. So the things I just want to highlight here are that beta basically appears to activate here at late time. So late time's on the left because there's a redshift plot. It appears to activate at late times. The reason it's doing that is because beta is essentially following the behavior of the derivative of the scalar field. So in the case of a cubic Galilean, beta happens to depend on the derivative of the scalar field. It doesn't actually depend on the scalar field itself, and that's to do with the fact that we only use x. The kinetic term is only composed of derivatives of the scalar field, not the scalar field itself. So we see here that beta is basically following the behavior of the derivative of the scalar field. So when the scalar field becomes significant, then this is reflected in beta becoming significant, and that basically means that the fifth force contribution becomes greater. So as the scalar field becomes relevant, obviously the fifth force contribution becomes more relevant as well. And similarly for the screening coefficient, the only thing I want to highlight here is that as the density increases, we see that the curve for the screening coefficient drops to 0. So we approach 0. And this is just telling us that as the density is higher, the screening coefficient acts in a way so as to suppress the fifth force contribution, and therefore the total force starts to look a lot more like just a Newtonian force, and therefore you only see GR-like behavior when the density is high. So when we have all those pieces, when we have the background data, when we use the background data to compute those various intermediate quantities needed to then compute the fifth forces, the total forces between the particles, we're then able to run the n-body part of HiCOLA, and then from the particle data we can compute the matter power spectra, and that's what we're showing here. That's what is shown here for the cubic Galilean. And so this is matter power spectra relative to GR in this case. So let's just discuss a few of the features being shown here. First of all, to the left of all of these curves, we can see that there's a roughly flat region for the curve. So this is the scale-independent, large-scale modification that the cubic Galilean predicts. We then see that there's a scale-dependent part where the curves all rise to a peak, and then they fall back down again. That fall back towards 1 is screening coming into effect. So we can see here that screening is activated, and as we get to smaller scales, the screening acts to suppress the action of the scalar field, and therefore we return to behavior that looks like GR. So here we are seeing that HiCOLA is showing us the effect of screening. But we can do more than that. We can also understand why the power spectrum looks the way it does. So we are able to break down the power spectrum and look at what constituent parts are giving rise to its overall shape. So what do I mean by that? We are able to isolate various effects on the power spectrum. So for instance, in the top left, that curve is meant to represent the isolated effect of just the modified background on the power spectrum. Similarly, on the right, we are isolating the effect of the unscreened fifth force. So this means that if we imagine the fifth forces of our cubic Galilean were never checked by screening and they were left unchecked, then how much is that contributing to the overall shape of the power spectrum? And then, of course, we can also isolate the effect of just the screening. How much is screening affecting the power spectrum shape? And also, what about the whole screen fifth force? How much is that affecting the power spectrum? So we're able to isolate these effects and understand how much of these effects are contributing. Today, in the interest of time, I will focus just on the modified background. What I want to highlight here is that, for instance, in the case of the cyan curve, so the cubic Galilean with the cyan initial conditions, we see here that the effects go up to as high as 25%. So just the modified background is enough to be responsible for up to 25% of that deviation away from GR. So what this is telling us is that for a cubic Galilean, the effect of the modified background alone is significant, and therefore this shows us the importance of considering the full modified background for these reduced Horndeski theories, particularly for the cubic Galilean at least, when it comes to doing this mildly nonlinear analysis. So we should not neglect the full modified background and assume it is, say, negligibly close to lambda CDM. Now, I said that HiCOLA is not designed to be very specifically just for one model. It's designed to be quite generic. So let's look at another member of the reduced Horndeski class. So here we're looking at what we've called the extended shift symmetric models. These were first studied by Träghofer and others last year. And they are specified by the following choices for K, G3, and G4 shown on screen. They basically look a lot like the cubic Galilean, but they have extra x squared terms. And the only thing I want to highlight here with these background curves is that the ESS models are able to match lambda CDM even more closely than the cubic Galilean. But how do their power spectra look? Well, you can see here that even though the background matches quite closely, the power spectra is actually quite different. The green model, model 3, goes up to deviations of up to 7.5%. So this is showing us that there's a rich theory space here. Even if you satisfy very lambda CDM-like behavior at the level of the background, at the level of the power spectrum, the differences are quite visible. They're able to be quite varied at these mildly nonlinear scales. And again, I will just repeat that the same features that were shown in the power spectrum for the Galilean are present here. So we have a large scale independent modification, and then there's a scale dependent rise towards the peak before screening activates and pulls us back towards GR. And so that brings me to the end of the talk. So I will just leave the takeaway messages up on screen for you. If you are interested in learning more about how HiCOLA works and what we have found through HiCOLA, we have written a paper and it's currently under collaboration review, so please do stay tuned. Thank you very much for listening.